Welcome to today's statistics tutorial. Today we will be covering confidence intervals. Be sure to see the links in the descriptions to get the online calculator that we will be using for this tutorial, as well as additional supports and resources.
Okay, let's go ahead and get started with Module 8, Confidence Levels. So up to this point, we have just solved for individual points, so such as the mean or standard deviation, and we just, because those are just a single point, those are called point estimates. A confidence interval is going to have, instead of just solving for a single point, we're going to be solving for an interval of points that we can say with a certain percentage that we have confidence that the true population parameter is going to be contained within that random interval. So when we did our population mean, our sample mean, we used the symbol X with a bar over that, and we find that by summing the mean, summing the samples divided by the total number of samples. And for our confidence interval, that's going to be in the notation of the sample mean plus or minus the error bound of the mean, which is the margin of error of that parameter. So we're going to subtract the error band to get our lower confidence interval point, and we're going to add it to get our upper bound. So what that means is that if I have a normal distribution, what we were previously solving for was the mean, which was just a single point. Excuse me. But with a confidence interval, we're going to start with, be given a confidence level, which will be some type of a percentage. So let's say this is 95%. Then the interval, and we want to know, we're going to say that with 95% confidence that the population parameter, the true population parameter, is going to be between these 2 points. And this first point here is going to be your lower confidence interval, and this point right here is going to be your upper confidence interval. And that's denoted by the X minus the mean plus or minus the error bound. Okay. So let's say we do not know what the population mean is, but we're given a sample mean of 7 and an error bound of the mean of 2.5. Then our confidence interval is going to be 7 minus 2.5 for the lower bound and 7 plus 2.5 for the upper bound. And that's going to give me a confidence interval of 4.5 for the lower bound and a 9.5 for the upper bound. And if we were given a confidence level of 95%, then our interpretation of this confidence interval would be, we would state that as, we estimate with 95% confidence that the true value of the population mean is between 4.5 and 9.5. Okay, any questions? Okay, let's get some more data. So now this error bound of the mean is going to be related to whatever the confidence level is. So let's go ahead and look at that, how to find that data. So the alpha is the parameter that we have the probability that that interval is not going to contain the unknown population parameter. So we can say that is 1 minus the confidence level. So if I have a confidence level of 95%, which we can write as 0.95, I can take 1 minus 0.95, and that's going to give me 0.05 or 5% as my probability that it's not the true population is not going to be contained within that 95% confidence level. And the blank area on the two sides of that confidence level that we've shaded in, those are your alphas. So we actually split alpha in half. So alpha in half, if I take 0.05 divided by 2, that's going to give me 0.025 or 2.5%. So this would be 0.25 probability on the right and a 0.025 on the left. That we expect that the population parameter is not going to be in those areas. Now the formula for the error bound an error bound of the mean for an unknown population mean and a known population standard deviation is going to be Z alpha over 2 standard deviation of the true population divided by the square root of the sample. And you'll recognize this standard deviation over the square root of the sample. That's what we did, we used with the normal distributions when we were using the central limit theorem. So that's where this comes from. And the notation, if we have a known, so this is a known population standard deviation, and that notation for that random variable is going to be N for normal distribution. Then we have the mean, and the mean of the population, which is going to be the same as the mean of the sample. The standard deviation of the population divided by the square root of the sample. So once again, this formula we got from Module 7 when we did the central limit theorem. Okay, and this standard deviation is called the standard deviation of the sample mean. It's also referred to as the standard error of mean. Now this is if we have a known standard deviation. Now, if we have an unknown standard deviation, population standard deviation, then we're going to use the student T scores instead of a Z score. And that formula is real similar. That is the error bound of the mean is going to have a T-score at the alpha over 2. times the standard deviation of the sample divided by the square root of the sample size. And you'll remember that the sample standard deviation is the formula that we used from Module 2. Okay, and so these are the two formulas for finding the error bound of the mean, whether you have a known population standard deviation or an unknown population standard deviation. Now, these are connected to our confidence intervals. So if I have a confidence interval of 95%, whoops, I didn't draw that very well. Start over with. Okay, so let's say this is 95%. This is my confidence level, and that's equal to 1 minus alpha. This is alpha divided by 2 on the outside. So once again, if I've got 95% on the inside, 1 minus alpha. 1 minus alpha, if I have 0.95, that's going to give me 0.05. Then if I divide that by 2, that's going to give me 0.025. So I've got 0.025 on this side and 0.025 on that side, and that's these blank spaces. So now to get my z-scores, this is going to be z at 0.025, and then this is going to be my negative z. Just like we did in Module 6, when we were calculating for z-scores, these are exactly the same thing. Now, if you remember when we did z-scores, the z-scores tell us the number of standard deviations away from the mean. And when we're calculating the standard, the z-scores, we're going to use standard normal distribution to figure out what those numbers are. So that means we're going to have a mean of 0 and a standard deviation of 1. So then we're going to go here to our normal distribution calculator so that we can solve what are going to be the z-scores if I have a 95% confidence level. So in order to solve for that, we're going to solve for it just like we did when we were solving for percentiles, when they asked you for what is the case percentile. So if they asked you for 95 percentile, we did this exactly the same way. So to solve for z, we're going to get 1 minus alpha over 2, which in this case is 1 minus 0.025. Which is going to give me 0.975. Now you'll notice that 1 minus alpha over 2 is the same as the confidence level plus alpha over 2. So that would be the same as 0.95 plus 0.025. That's going to equal 0.975. So what we're solving for is we're solving for this z right here, the positive z. And if you'll remember, so the confidence level is all this stuff in between the 2 points. But if I want to find z, then I want everything to the left. So that's going to include the confidence level plus one of these alpha over 2, because we're trying to solve for this point right here. Okay? So now I'm solving for the probability where the value of where z is going to be greater than 0.975. So I'm going to go here to my calculator, normal distribution, mean of 0, standard deviation of 1, and we're going to do the inverse probability, 0.975. So remember, we're putting in the values for the standard normal distribution. That's where the mean of 0 and standard deviation came from. Calculate. The number in red is going to give me my z-score. So my z-score, when my confidence interval is at 95%, it's going to be 1.96. So this is important to remember. This z-score of 1.96 is always going to happen when I have a confidence level of 95%. These two come together. So whenever you have a problem that says you're given a confidence level of 95%, then you're automatically going to have the z-score of 1.96. So all you have to do is solve this once, and if you can remember this number, then you can just plug that value in. You don't have to re-solve for it. Okay? Now let's do the same thing, but with an unknown population standard deviation. So now if I have an unknown population standard deviation, I'm going to use this t-distribution, known as student t-distribution with blank degrees of freedom. Now the difference here, so let me go ahead and let me make sure I have enough room to draw this. Okay, so I'm going to just draw this in the space up here above. So let me explain the difference here a little bit. So let's say if I have a known population standard deviation, then it's going to follow the ideal, which is a normal distribution curve. But most of the time, we don't know what the population standard deviation is. And in that case, we're going to need to use the sample standard deviation. Now, if our sample size is small, then we're going to have low probability that we're going to match the ideal, we're going to get it accurate. It's likely to be a little bit thicker at the tails and maybe not quite as high. The closer we get to the larger the sample size, the closer we're going to get to achieving that same normal distribution. So that's what the t distribution, that's what it adjusts for. It adjusts for if we don't know what the population standard deviation is, and it's especially helpful if we have small sample sizes. Okay, any questions about that? Okay, so let's plug in the formulas and see how it differs. So if we have a known population standard deviation, we're going to have at 95% confidence level, we're going to end up with a z-score of 1.96. So let's see how that differs if we don't know what our population standard deviation is. So once again, in order to figure out this t-score, we're going to use a t-distribution. So we're going to use the t-distribution with the standard normal distribution parameters. So you're going to use the t-distribution. And we're going to use the parameters of the mean being 0 and the standard deviation of being 1. Oops, and I wrote that back. And then once again, we're going to do the same thing where I have the probability, where we're looking for t. And if we're given a confidence level, so we're going to do the same thing where we have a confidence level of 95%. So those parameters are going to be the same. It's going to be 1 minus the confidence level. So once again, that's going to be the exact same thing, 0.975. So all of this data is exactly the same as what we did with the z-score. Those numbers all stay the same. Now, with this, because we're doing the t-distribution, we need to know what the degrees of freedom are. And the degrees of freedom are dependent on the sample size. So the degrees of freedom is going to be n minus 1 degrees of freedom. So if my sample size, let's say my sample size is 15, actually let's make it small. Let's say my sample size is 5, then my degrees of freedom would be 5 minus 1, which equals 4. So I'm going to put that up here in this box up here. I'm going to put a 4. Everything else stays the same. Calculate it. And that's going to give me a t-value of we'll say 2.78. So you can see that when I use my normal distribution, I got 1.96, but if I have a really small sample, then my t-score is going to be 2.78. So my variation, or the number of deviations away from my mean is going to be a lot bigger. So let's see what happens if I have a sample size of 500. Then my degrees of freedom are going to be 500 minus 1, which is going to be 499. So let's bring that up to 499. Everything else is the same. We calculate, and there we go. Now we've got a t-score of 1.96. So when I have a large sample size, so when I have my sample size is 500 or greater, then my t-score is going to be similar to my z-score. So this distribution, this graph is going to look very similar to when I had a known population standard deviation. Okay, any questions about when you have a known or unknown population standard deviation? Okay, so now I'm going to get another board, and we're going to do the same thing, and this time with a confidence level of 90%. So your confidence levels, most of your problems, and both on your homework and in real life, they're going to use a confidence level of either a 90 or 95%, most likely. But it's So it's good to know what these z-scores are and how to solve for them. But on occasion, you might get something different. So it's good to know how to solve for them. So let's go ahead and get a new board. Okay, so now let's do the same thing, but this time with a 90% confidence level. So let's draw a little graph to see what that looks like. It's going to look real similar to what we just did. This time your confidence level is 0.90. So once again, your confidence level is 1 minus alpha. And that's everything on the inside here. Then these blank edges on the outside, they're going to have a value of alpha over 2. So if I have a confidence level, so if my confidence level is at 90 and I want to solve for alpha, that's going to be 1 minus 90, which is going to give me a 0.10. That's going to make my alpha over 2. 0.10 divided by 2 is going to give me 0.05. So these are 0.05, 0.05. So now my z, and this is going to be your spot for either your z or your t, depending on if you have a known standard deviation or not. So this is z of 0.05. So then I have, so this is for a known population standard deviation. So once again, I'm going to find my value for my z-score. That's going to be 1 minus alpha over 2. So that's 1 minus 0.05. So that's going to be 0.95. I'm going to change that here, 0.95. We're going to have, if I have a known standard deviation, then I'm going to use a normal distribution with a mean of 0 and a standard deviation of 1. I'm going to go back to normal deviation. Mean is 0, standard deviation is 1. We're using the inverse probability at 95%. Calculate. That's going to give me a z-score of 1.645, and this is for confidence level 0.90. So once again, remember these two values are going to go together. So if you have a known population standard deviation and they give you a confidence level of 90%, your z-score is always going to be 1.645 that you're going to use when you're calculating your error bound of the mean. So now let's look at if we have an unknown population standard deviation, then we're going to use the t-distribution with n minus 1 degrees of freedom. Once again, let's say we have a confidence level of 90%. That means our p, the probability for our t-score, is going to be 0.95. So it's just the same as what we did with the z-scores. Now we're solving for t-scores. We're going to use a mean of 0 and a standard deviation of 1. And then the only difference, because we're using the t-distribution, we need to determine sample size. We need to determine the degrees of freedom. So once again, let's say I have a sample size of 5. Then my degrees of freedom is going to be 5 minus 1, which equals 4. So if I have an unknown population standard deviation and a sample size of 5, then my t-score is going to be 2.13. And as you can see, that's a lot bigger than the 1.645 that we have with our ideal normal distribution when we have a known population for standard deviation. Now let's see what happens when we use a larger sample size. So if I say n equals 500, my degrees of freedom is going to be 500 minus 1, which equals 499. And then once again, our t-score with the larger sample now is the same as our z-score of the normal distribution with a known, actually that's not quite right, but it's possibly close. So it's not exactly the same, but it's pretty close. It's a lot closer than at the 5. And let's see what happens if we have 1,000, which would be 999, then we're even closer. So if we went here, we've got n equals 1,000. Our degree of freedom would be 999, and our t-score would be 1.646. So we're getting, as we get bigger, we're getting closer to what the z-score is. Any questions? Okay. Now let's do the calculations for the error bound. Let's look at those formulas. So the formula for, so let's just write, just to put everything on the same page. So we had the z-score for confidence interval 90% was 1.645. And then the z-score that we did on the last board was 1.96 when we had a confidence level of 0.95. So we've got both of those there. So now let's look at the error bound of the mean. So the error bound of the mean, the formula is going to be your z-score for the alpha over 2 at that point times the population mean divided by the square root of the sample size. So remember that came from the central limit theorem. So if I have a 95% confidence level, then that's going to be 1.96 times the standard deviation over the square root of the sample. And if I have a 90%, then that is going to be 1.645 times the standard deviation over the square root of the sample. Okay, so this is at 95% confidence level, and this is at a 90% confidence level. This is the formula you're going to use. And then if you have your error bound, if it's unknown, your error bound of the mean is going to be the t-score times the sample standard deviation divided by the square root of the sample size. Okay, any questions? Okay, let's do some examples so we can see how this comes together in practice. So we're given a normal distribution with unknown population mean and a population standard deviation of 3. We have a sample size of 36. A sample size of 36 and a sample mean of 68. And we want to find a confidence interval estimate for the population mean. Let's say we're given a confidence level of 90%. So if I'm given a confidence level of 90%, I have a known standard deviation. What does that automatically tell me that my z-score is going to be? And you can either type that in the chat box or go ahead and unmute yourself and tell me what that's going to be.
Points.
Yep, perfect. Okay, so my z-score is going to be 1.645, and since we already solved that, that saves us some time for figuring that out. Okay, so now all we have to do is figure out what our error bound of the mean is for this particular set of data. So the error bound of the mean, the formula is going to be your z-score times the population standard deviation divided by the square root of the sample size. So that means I've got 1.645 multiplied by 3 over the square root of 36. That's going to give me 1.645 divided by 3 over 6, which is 1.645 times 1/2, which will give me 0.8225 as my error bound of the mean. Now my confidence interval is going to be the mean plus or minus the error bound of the mean. So that means I'm going to have 68 minus 0.8225 for my lower bound, and 68 plus 0.8225 for my upper bound. And that's going to give me a confidence interval of 67.1775 and 68.8225. So if we had a graph, this would be 90%, and this would be my upper bound of 68.8225, and this would be my lower bound right here of 67. So this would be the 67.1775, and this would be my 68.8225. So then what we can say for our interpretation, we say we estimate with 90% confidence that the true population mean is between 67.18 and 68.82. Any questions? Okay, let's do it again, but this time, let's say I have a confidence level of 95%. What is my z-score going to be?
1.96.
Good job, 1.96. Okay, so now we're going to plug that into the error bound of the mean measurement. So that's going to be 1.96, and we already solved for the standard deviation divided by the square root of the sample, which was 1/2. So that's going to give me 0.98. So now I'm going to do my confidence interval, which is the mean plus or minus the error bound of the mean. So that's going to be 68 minus 0.98 for my lower bound and 68 plus 0.98 for my upper bound, which will give me 67.02 for my lower bound and 68.98 as my upper bound. And so then we can say we estimate with 95% confidence that the true population mean is between 67.02 and 68.98 on our graph. So you can see that when I do my second one, so and actually I'm gonna, this graph is kind of small, but if we do it here, so we have, let's say we have in black is the 90%, and then we want 95%. We see that it's going to make that interval just a little bit smaller. This is 68. Actually, that shifted that. Make sure I got these numbers right. So that's going to shift that just a little bit over, and that's going to shift that. So it's going to make that interval just a little bit smaller. It also, if you notice, for this particular example, it actually shifted it just a little bit. Okay, any questions? So when we reduce our percentages, then our interval is going to get smaller, which is what we would expect. Okay, so now let's do the same type of problem, but this time with unknown. Let's do this with an unknown population. So this is when we're going to use our t-scores. And over that. So an example. So let's pull out an example here. Okay, so if I have this sample, there we go. See if it'll let me make it bigger. You can actually see it. Okay, so with this one, it says a random sample of statistics students were asked to estimate the total number of hours they spend watching television in an average week. The responses are recorded in this table. Use the sample data to construct a 98%, I thought, actually, this is fine, to construct a 98% confidence interval. So this one tells us we're going to have a confidence level of 98%. So that tells us we're going to need to use slightly different information than what we did before, but everything's going to solve exactly the same way. And then we want to find the mean number of hours statistics students will spend watching television in 1 week. Okay, so they gave us the confidence level, and that's the only thing that we know. So that tells us if that's all they give us, then that tells us we're going to need to use the t-distribution because we aren't given the population standard deviation. So the first thing we're going to do is count the number of data, and that will give us our sample size. So this one, we have a sample size of 15. That means my degrees of freedom is going to be 15 minus 1, which equals 14. The next thing I need to do is I need to find my sample mean. And if you remember from Module 2, we get the sample mean by summing all of the data values divided by the number of data. So that's going to give me 92 divided by 15. It's going to give me a mean of 6.133. My sample standard deviation, remember you have a sample, you're going to use the small s instead of the sigma. And that formula is the square root of the sum, of your x value minus the mean quantity squared divided by the sample size minus 1. And when we plug all of our data, into that formula, we get a sample standard deviation of 5.514. And we're going to need to calculate that 98%. So I'm going to put my calculator back up. I've got a confidence level of 0.98. So that means my alpha is going to be 1 minus the confidence level, which is going to be 0.02. That's going to make alpha over 2 equal to 0.01. So now I need to solve for t. So I'm going to have the probability that x is less than t is going to equal 1 minus alpha over 2. So that's going to be 1 minus 0.01, which is going to equal 0.99. So I'm going to plug in 0.99 here in my probability graph, in the inverse probability. And once again, when you're solving for your t-scores or your z-scores, you're going to use a mean of 0 and a standard deviation of 1. And then we have a degrees of freedom because we're using the t-distribution. We solved that up there. We solved that right here. That's going to be 14. So I'm going to put in 14. I have my mean of 0, standard deviation of 1. Solving for 99th percentile, that's going to give me a t-score of 2.624. Okay. And just for funsies, let's see what it would be if I had a normal distribution. If I was doing the normal distribution with a known population standard deviation, my z-score would be 2.326. So you can see that there's a little bit of variation between our t-score and our z-score. So now I need to find my error bound for the mean. That's going to be my t-score times my sample standard deviation divided by the square root of my sample size. So that's going to be 2.624 times 5.514 divided by the square root of 15. And when I plug all of those numbers in, I end up with 3.7355, which I can round up to 3.736. And then I'm going to get the confidence interval, which you'll remember is the mean plus or minus the error bound of the mean. So that's going to be, we have a mean of 6.133 minus 3.736 for my lower bound is 6.133 plus 3.736 for my upper bound. And that's going to give me, excuse me, that's going to give me a confidence interval of 2.397 for my lower bound and a 9.869 for my upper bound. So then we can say we estimate with 98% confidence that the mean number of all hours that statistics students spend watching TV in 1 week is between 2.397 and 9.869. Okay? Now let's do the same thing, but this time let's use a confidence level of 90%. Let's see if I can put this on the same screen. Okay, so I'm going to do this in green. And I'm going to keep it here so we have all of our data the same. So let's say I have this time I have a confidence level of 90%. All of my other data is going to stay the same. So this time my alpha over 2 is going to be 1 minus the confidence level divided by 2. So that's just 1 minus 0.90 divided by 2, which is 0.10. 10 divided by 2, which equals 0.05. Then when I'm solving for my t, that's going to be 1 minus alpha over 2. So 1 minus 0.05, which is going to make that 0.95. So now we're, instead of 0.99, we're going to have 0.95. Everything else is going to stay the same because we have 14 degrees of freedom. We're going to use the mean at 0, standard deviation at 1. We're finding the 95th percentile. That's going to give me a t-score of 1.761. So you can see the t-scores, compare them. So when I have a 90 percentile, my t-score is 1.761. And then when I had a 98 percentile, my t-score was 2.624. So that's going to change my values quite significantly. So now let's plug it into the error bound of the mean. So that's my t-score times the sample standard deviation divided by the square root of the sample. And when I plug those numbers in, I end up with 2.508. So my error is 2.5. My error margin is going to be 2.5. And with the higher probability, I had an error margin of 3.73. So now let's go ahead and put those in the confidence intervals. So once again, that is going to be x plus or minus the error bound of the mean. So that's going to be 6.133 minus 2.508 for my lower bound, and 6.133 plus 2.508 for my upper bound, and that's going to give me 3.625 for my lower bound and 8.641 for my upper bound. And so with this data, we can say we estimate with 90% confidence that the true population mean is going to be between 3.63 and 8.64. Any questions? Okay, let's go ahead and move on to proportions. Okay, so when we're looking at population proportions, we're going to use the binomial distribution. The binomial distributions don't have a mean or average. If you remember from Module 5, the notation for a binomial distribution is n, comma, p, where n is the number of trials and p is successes. So if you remember with a binomial distribution, that's when you just have two possible outcomes. Either you're going to have a success or a failure. So oftentimes these type of studies would be like a true-false or yes-no, something that is going to be just black and white. You can either have a success or you have a failure. So for confidence intervals, we're going to redefine some of these distribution terms so that we can solve for an interval rather than a point estimate. So we're going to have p hat or p prime is going to be our new variable for our successes, and that's defined as x over n. So p prime is the proportion of successes, and the x is the random variables for the number of successes, where n is the number of trials. When n is large and our p does not equal 0, 1, then we can use a normal distribution to approximate the binomial. And that's going to change it to x n of n times p and pq, which you can remember is the notation for a binomial. It's notation for a binomial when you use the normal distribution property. Your mean is going to be equal to n times p, the number of trials, times the number of successes, and your standard deviation is going to be the same as the square root of the number of trials times the number of successes times the number of failures. This is all from the binomial distribution. And then to get our estimated proportion, we're going to take x divided by n, and that is going to equal to your p prime. And that can be written as the normal distribution in p over n and the square root of n p q over n. And then just simplifying that, that's going to give us the p prime is going to be n p, the successes, and then these cancel out to be the square root of pq divided by n. And our confidence interval for when we're dealing with proportions is going to be the p prime, which is your estimate of successes, plus or minus the error bound of the proportion. And the formula for the error bound of the proportion is going to be the z-scores that we calculated before times the square root of p prime q prime over n. So it's just like what we did before. It's your z-score times your standard deviation that we're calculating. And this is your Q, which is Q prime, which is the estimated portion of failures, is just going to be 1 minus P prime, which is just the same as what it was when we did our binomial. And your P prime which we have up here already, which equals x over n, is the estimated proportion of successes, where p prime is a point estimate for the true proportion. X is the number of successes, and n is the sample size. And p prime and q prime are estimates of the unknown population proportion because the exact probability of successes and failures are not known. Okay, so p prime is the estimate portion of success, q prime is the estimated portion of failure. Now, in order for this to be true, n times p prime has to be greater than 5, and n times q prime also has to be greater than 5 in order to use the confidence intervals. And your z-scores, which we found before, that can also be calculated doing p prime minus p divided by the square root of p, q, and n, where p prime is the estimate, and then the p's are the probability of successes, q is the probability of failure, and n is the number of trials. Okay, let's do an example. Let's see, we'll do an example. It's going to let me get a picture. There we go. Okay, so suppose that a market research firm is hired to estimate the percentage of adults living in a large city who have cell phones. 500 randomly selected adult residents in the city are surveyed to determine whether they have cell phones. Of the 500 people surveyed, 421 people responded yes, they own cell phones. Using a 95% confidence level, compute a confidence interval estimate for the proportion of adult residents of the city who have cell phones. So this has told us that we have sampled 500 people, so that means our sample size is 500. The number of successes is going to be 421. That's the number of people that responded yes. We want a confidence interval of 95%. So what does that tell me my z-score is going to be?
96.
Good, 1.96. Good job. And then, so that's what is given, and it tells us that they want to know the proportion. So we know that it's binomial because the survey was wanting to know just yes or no answers. And then we know we're going to be solving for proportions because that's what they're asking for in the question. So that means I have x, so we're going to let x equal the number of people in the sample who have cell phones. X is going to be a binomial, so we're going to use the notation x binomial n over p. Now our p prime is going to be, so remember our p prime is going to be x divided by n. So that's going to be 421 over 500. So let's write that out. So X binomial is going to be N over P, or N and P. So when I write it with this data, it's going to be the N is going to be 500, and my P is going to be 421 over 500. Okay, so our P prime, which is our estimated proportion of success, is going to be the number of successes divided by the number of trials. That's 421 divided by 500. When I solve the math, that's going to give me 0.842 for my proportion, estimated proportion of success. Now Q, my estimated proportion of failure, is going to be 1 minus P prime. So that's going to be 1 minus 0.842, which is going to give me 0.158. That's my estimated proportion of failure. We've already got our confidence level of 0.95, which gave us a z-score of 1.96. So now we can find our error bound of the proportion. Which is going to be your z-score times the square root of p prime q prime divided by n. So that's going to give me 1.96 times the square root of 0.842 times 0.158, all divided by 500. And then when I do that math, I end up with 0.032. Any questions how I got that? Okay. So now let's do our confidence interval. So remember, our confidence interval is going to be P prime plus or minus the error bound of the proportion. So my P prime is 0.842 minus the error bound, which is 0.032. Then my upper bound is going to be 0.842 plus 0.032. And that's going to give me 0.810, 0.874. Now, when we are dealing with proportions, we're going to be using percentages rather than just points. So this 0.801, that's the same as 81%. And my upper band is going to be 87.4%. So when we do the proportions, we're going to refer to them, our confidence intervals, in percentages. So when we do our interpretation, we say we estimate with 95% confidence that between 81% and 87.4% of all adult residents of this city have cell phones. Okay, any questions? Okay, let's do another one. Okay, so for this next one, let's say we have a class project, a political science student at a large university wants to estimate the percentage of students who are registered voters. He surveys 500 students and finds that 300 are registered voters. Compute a 90% confidence interval for the true percent of students who are registered voters and interprets the confidence interval. So we're given a confidence level of 90%. So what does that mean my z-score is going to be? I have a 90% confidence level. What will my z-score be?
1.645.
Good. 1.645. I'm given 500 students. And I've got the number of successes. Number of successes are 300. That's going to give me a p prime is going to equal x, my number of successes, over number of trials. So that's going to be 300 over 500, which is going to give me a 0.600. You can also just say 0.6. That means my Q, my estimated number of failures, is going to be 1 minus p prime. 1 minus 0.600 is going to give me 0.400. You can also just write that as 0.4. Now my error bound of the proportion is going to be my z-score times the square root of p prime q prime divided by n. So that's going to give me 1.645 times the square root of 0.6 times 0.4, all divided by 500. So that's going to give me an error bound of the proportion is going to be 0.036. So then I'm going to get my confidence interval, which is going to be my p prime, which is my estimated portion of success, plus or minus the error bound of the proportion. So that's going to be my p prime, which is 0.6 minus 0.036 for my lower bound, and then 0.6 plus 0.036 for my upper bound. That's going to give me a 0.564 for my lower bound and a 0.636 for my upper bound. And once again, we're going to write these in terms of percentages because we're talking about proportions. So that's going to be 56.4% for my lower bound, 63.6 for my upper bound. And then our interpretation is we say we estimate with 90% confidence that the true percent of all students that are registered voters is between 56.4% and 63.6%. Okay, any questions? Okay. Let's do another board. Now, when we're dealing with proportions, if the sample size is really small, then sometimes we need to do what is called the +4 confidence interval for P. And this tends to make things more accurate when your sample sizes are small. And so what you do with that is we're going to add whatever your n value is, we're going to add 4 to that, and we're going to add, and with that, by adding 4 extra samples, then we're going to say we have 2 additional P's, successes and 2 additional failures. So all we're doing with that is we're going to say we're going to add 4 observation trials, 2 are successes and 2 are failures. So because those will cancel each other out, all we're doing is just making all of our data bigger so that it will be closer to the true population. Because as we saw before with when we were solving for the t-scores, the larger our sample, the closer to the actual populations we're going to be. So let's say we have let's do another sample. Okay, so for this one, let's say we have a random sample of 25 students were asked, have you smoked a cigarette in the past week? Six students reported smoking within the past week. We want to use the +4 method to find a 95% confidence interval for the true proportion of statistic students who smoke. So with this one, we're given a confidence interval of 0.95. So that tells us our z-score is going to be 1.96. We have a random sample of 25 students and a success of 6. So now what we're going to do is we're going to take this n, we want to take n plus 4. So now instead of 25, we're going to take 25 plus 20 plus 4 to make our sample size be 29. And we're going to take our x's of 6, our number of successes, which was 6, so our number of successes was 6. We're going to add 2 to that to make that 8. Everything else is going to be solved exactly the same. All we did is we just made those 2 data points bigger. So now I've got p prime is going to equal x over n, and I'm going to use my +4 adjustment. So that's going to give me 8 over 29 for my estimated proportion of success, which is going to give me a 0.276. My q prime, my estimation of failure is going to be 1 minus p prime, so that's going to be 1 minus 0.276. So that's going to equal 0.724. So now I'm going to find my error bound of the proportion, which is going to be my z-score times the square root of p prime q prime divided by n. So that's my 1.96 times the square root of 0.276 times 0.724. 724, all divided by my adjusted population, or my adjusted sample size of 29. And when I calculate all of that, that's going to give me 0.163. So now I'm going to put it in my confidence interval formula, which is P prime, the estimated proportion of successes, plus or minus the error bound of the proportion. So that's going to give me 0.276 minus 0.163 for my lower bound, and 0.276 plus 0.163 for my upper bound. That's going to give me 0.113 for my lower bound, 0.439 for my upper bound. Once again, with proportions, we write those in percentages. So that's going to be 11.3% and 43.9% for my upper bound. So with our interpretation, we write, we are 95% confident that the true proportion of all students who smoke cigarettes is between 11.3% and 43.9%. Okay, any questions? Okay, so we've covered how to solve for the three different types of confidence intervals. Now, using the principles of algebra, sometimes they will want you to work backwards. They'll give you some information and then they want you to find. So let's say, well, since we're doing proportions, we'll start with proportions. So let's say we wanted to have a specific margin of error. So that would be our error bound for the probability. And we wanted to do a study where we wanted to have a specific error margin. Then we needed to figure out how big our sample size needs to be in order to have that. So here would be an example. So if I have my error bound of, so this, remember our formula is our Z times P prime Q prime all over N. Then if I wanted to solve for N, then I just using algebra, I'm just going to move stuff around. That's going to be, so I'm just swapping the square root of N and the error bound of the portion. So that's going to give me Z square root P prime Q prime divided by the error bound of the portion. And then because we want N, not the square root of N, then I'm going to square both sides. So to get N, I'm going to want the square we're going to square both sides. And that's just going to give me, that's the same as saying Z squared P Q. And this should still be P prime Q prime. And the error bound of the proportion is also going to be squared. So let's look at an example. And this one's a little bit longer. And these examples all come from your book. Okay, so this one says, suppose a mobile phone company wants to determine the current percentage of customers age 50 plus to use text messaging on their cell phone. How many customers age 50 plus should the customer survey in order to be 90% confident that the estimated sample portion is within 3 percentage points of the true population of customers age 50 to use text messaging on their cell phone. So for this example, so we've got our formula for solving for n. So we're going to have a confidence level of 0.90. So that tells me my z-score is going to be 1.645. And it says we want the estimated sample proportion to be within 3 percentage points of the true population proportion of the customers. So they've written it out in the words, but what that's saying is that's your error bound of the proportion. So they want the error bound of the proportion to be 3%. So if I write that as a decimal, I'm going to move the decimal 2 places. So that's going to be 0.03. Okay, now this one, it didn't give us our P prime or Q prime. And part of why I included all of this sample is because if they don't give it to you, then you have to figure out what's going to give me my best result. So for this one, since we don't know what P prime is going to be, and we're going to have to multiply P and Q together, then we get our largest possible product if we make them both 0.5. And you could try using other variations to see what you end up with. But if you make them equally likely, you'll get the highest, you'll get a 0.25. So for this, we're going to use our P prime as 0.5 and our Q prime as 0.5. Any questions as to how we got that? Because that's a little confusing. Okay? Because we want, when we're trying to figure out what the sample size is, we want to figure out the numbers for what's going to be as large as possible. Okay, because we want to get the largest possible n. That part, largest possible sample size. So now we've got all of our data and we just need to plug that in. So I have n equals z squared p prime q prime divided by the error bound of the proportion squared. So that's going to give me 1.645 squared times 0.5 times 0.5 all over 0.03 squared. And then when I do all of that calculation, I'm going to end up with 751.67. Now, whenever you're trying to figure out sample size, you're always going to round up to the nearest integer. So for this, our sample size is going to be 752, is the sample size that this study is going to need in order to have an error bound of error of margin of 3%. Now, it's important to recognize that if, let's say, we came up with a result of 751.02, if we followed normal rounding procedure, then we would just round down to 751. But if we're looking for sample size, if we've got anything left over, we're going to round that up and make that 752. because we want to make sure that our study is large enough to get the results we want. And all this number is telling us is that we've got a partial person. And since you can't really have partial people, then we're going to round up and make them a whole person. And it's better to have a little, an extra person or two in your study for when you're collecting data than to have it small and than to have your study too small. Okay, any questions? Okay, now we're going to do the same type of concept, but with your confidence intervals when we use your other formulas, or if you had, let's say they gave you the confidence interval, but you wanted to find what was the mean or the error of measure. So let's get a new board. So let's say instead of giving you the mean and standard deviation or mean and error bound and asking you to solve for the confidence interval, let's say they did the reverse. They gave you the confidence interval and wanted you to find the mean or the error bound of the mean. So let's look at what our formulas are, and then just using algebra, we can kind of switch things around. So if I have my confidence interval, which I'm just going to label as CI, that is going to be the mean plus or minus the error bound of the mean. So we have, that tells me that the lower level of the confidence interval is going to be the mean minus the error bound of the mean, and my upper bound is going to be the mean plus the error bound of the mean. So just using algebra, we can move these numbers around. So if I wanted to solve for the mean, then I can just switch these sides and let I can add the error bound of mean to both sides and take the lower limit and add the error bound, and that's going to give me my x value. If I wanted to find the error bound of the mean, I could do just the opposite. And then once again, I can do the same thing with this other formula where all I'm doing is moving these values down like you're solving for x, just like we did for in algebra. We're going to move these guys around. The upper limit, we're going to subtract. You're going to do just the opposite. And then if I have my error bound of the mean, the upper bound. So you can just, and all this is just solving for x, subtracting or adding one thing to the other side so that we have we're solving for a different variable. Any questions? The other thing you can do is if I have, because we know that the upper and lower limits, we can solve for, let's say you were given the upper and lower limits, then you can add, and we needed to solve for the mean. The mean is also the average or the middle spot between the upper and lower confidence intervals. So we can just add the upper and lower together, divide them by 2, and that's also going to give us the mean. So let's do an example. So let's, using what we did, using our example, the first example we did, where we ended up with a confidence interval. We had a confidence interval of 4.5 and 9.5. Then I can solve for my mean by taking that average, 4.5 plus 9.5 divided by 2. That's going to give me 14 over 2, which equals 7, which is what we had for our initial problem. And then I can solve for my error bound of the mean by taking that upper limit of the confidence interval and subtracting the mean, and that's going to give me the error bound of 2.5. So if you remember from the very beginning of the lecture, this is what we were initially given, was a mean of 7 and an error bound of 2.5, and then we found the confidence interval of 4.5 and 9.5. So just using algebra, you can do the reverse. Okay? Now let's say that a study wants to have a specific error of measurement. Then we can solve it. So then we want to solve for, and so we want to know what sample size we're going to need in order to get that error bound. So once again, like we did with portions, you have your formula for your error bound, which is your z-score times your standard deviation divided by the square root of n. So then if I want to solve for n, we just move those numbers around. That's going to give me my z-score over sigma divided by error bound of measurement, error bound of the mean. Then we're going to square everything to get n. That's squared. So let's say they give me an error bound of 2, a standard deviation of 15, and confidence interval of 95%, which is going to mean that my z-score is going to be 1.96. Then all I have to do is plug in all of those numbers to solve for n. So that's going to be n is going to be the square of 1.96 times 15 divided by 2, and all of that is going to be squared, and that's going to give me 2.16.09. But once again, because we're solving for n, we're going to round that up to a sample size of 2.17. Any questions? Okay.
Don't standard deviation for that. What if they only give you the confidence level and the margin of error?
And they want to ask for your, and they're trying to figure out the sample size. I don't think they would give that to you. They should give you everything. I was going to say, if you had your, yeah, and even with the, that, you know what, in order to do that, you would have to, because if you're looking at your, if they don't give you your the standard deviation, let's see, because your t-score,
Looking at a problem, candidate has asked you to conduct a poll to determine what percentage of people support her. If the candidate only wants a 4% margin of error at a 95% confidence level, what size of sample is needed?
okay, so let's work that problem out. Okay, so give me all the data. What is the data?
95 confidence,
Okay,
which would mean that the z-score would be 1.96,
good.
and the margin of error is 4%.
Okay, so if it's 4%, what is that going to be as a decimal?
0.0.
Good. Okay,
And
that's all it gave you?
yes.
And it wants to know the sample size.
Yeah, what size of sample is needed?
Okay, and okay, read this problem to me one more time.
A political candidate has asked you to conduct a poll to determine what percentage of people support her. If the candidate only wants a 4% margin of error at a 95% confidence level, what size of sample is needed?
Okay, so this one, this one is going to use your formulas for your proportions. So let's go back and look at that board. So this one, when we were solving for n, so this is actually where that information goes, because this is going to be your portion of successes and failures. So let's plug that in. So we had, okay, give me those numbers again. So we have what, a 95%? 95%, and which gave us a z-score of 1.96, and they gave you an error of margin of 4%, which is 0.04. Okay, so this is your clue. So he's wanting to know, they're wanting to know who's going to vote him, how many people are going to need to vote for him. So the first cue is they didn't give you a standard deviation. The second cue is that they're wanting to know what percentage of sample that will vote for him. So that's going to tell you it's going to be a binomial, because it's either yes, they're going to vote for him or her, or no, they're not. Do you see how that's worded in the problem? And I don't have the problem right in front of me, so I know I'm tripping on some of the words. Does that make sense as to why we're going to use this formula rather than the other one?
Yeah, makes sense.
Okay. So now, and they didn't give us our P prime or Q prime, because that's what we would want to know. That would be the other piece of information. So it's going to be exactly like we did with this cell phone problem. Because they didn't give us the P prime or the Q prime, then we're going to go with what's going to give us the biggest value. So if they don't give you the proportion of successes and the proportion of failures, and it looks like it's going to be a binomial proportion type question, then you're going to split these even as in 50-50. Because that's going to give you, multiplied together, that's going to give you 0.25, which you can see here in this little example, when they gave a few examples, that 0.25 is going to be the biggest. But you can also experiment with that and try what are all different probabilities. So if I have successes as 0.6 and failures is 0.4. If I multiply that together, that's going to be 0.24. And that's smaller than 0.25. And when I want a sample, I want it as big as possible, because that's going to give me the best result. Okay? So now you have everything you need in order to plug in your little formula. So now we just plug that in. We've got our Z. So that's 1.96 squared. Our P is going to be 0.5. Our Q is going to be 0.5. And our error of margin is going to be 0.04 squared. And then you're just going to put all of those numbers in your calculator, and we can figure out what that is. Okay, so when you do all that math, what number did you end up with?
I'm pulling up my calculator.
Yep, no problem.
$600.25.
Yep, that's what I got.
So they'd need 601.
Yep, exactly. So we need a sample size of 601 in order to get that error, 4% error of margin. Okay, good question. Any last questions before we wrap up for today?
So.
Okay, excellent. Very good questions, and thank you for coming again.
Thanks for watching. I hope you found this helpful. Be sure to like and subscribe to get the latest videos by Caz Academy, and we'll see you at the next video.